Hi. Hello. Today I'll be doing my assignment for effective presentation and teaching, and I'll be teaching Cauchy sequences. So let's begin with what are sequences itself. Sequences are nothing but a function defined from natural numbers to real numbers. These can be just your normal natural numbers themselves, like 1, 2, 3, 4. That is a sequence, or some other sequence, say the n digits of pi. So you can start with 3 and then 3.1, 3.14, and so on and so forth. So this is the most generally accepted definition of sequences, whereas there are other specific definitions depending on situations, but this will suffice for our discussion. Uh, to say a sequence converges means that there is some value, and whatever this value, some arbitrary value, and you have sufficient number of you have this sequence of numbers that you have getting arbitrarily close to this specific value. What is the meaning of this is, in a slightly more formal sense, is that if I take any neighborhood around this value that it's converging to, there is infinite number of points of the elements of the sequence. This can be sort of geometrically interpreted is if I have a point of convergence and I am approaching this point, the sequence is approaching this point. To converge to this point, that means there are, regardless of however small a circle I draw around the point of convergence, there are infinitely many elements of the sequence that are there in that circle. If that is not the case, you run into the issue that you're not converging to this point because you're moving away at some point. The sequence is moving away from this. The geometric interpretation of is in some sense can be given by that. Another very important question to ask is, instead of saying, oh, okay, it converges to some point X, how is it behaving with each other? So if I take some nth element of the sequence and mth element of this, n and kth element of the sequence, how close are they getting as we increase n and k is a very important question that can answer a lot of other properties that sequences usually hold. And this is an important question that was asked by Augustus Cauchy himself, asking how does this behavior matter? So how close are these elements getting to each other in the sequence as you go further, as you increase n and k later on? A slightly more formal understanding of this is that if I have an arbitrary neighborhood that I define around some point n, some nth element of the sequence, what can I talk about whether a kth element in the sequence belongs to this neighborhood around the nth element, or does it not? It's an important question to ask, which is sort of what leads us to the idea of Cauchy sequences. So if I have a sequence an where n is the index of the sequence, and if let's say the sequence has the following property that for some capital N, some natural number capital N, if I draw any arbitrary neighborhood around a specific a small n, such that this small n is larger than capital N, then all elements of the sequence after n are in this neighborhood, after capital N are in this neighborhood. A slightly more formal way to define this is that for any given neighborhood, there exists a capital N such that all n comma m greater than this n, am, which is some element in the sequence, will be in the neighborhood of an, where this neighborhood is this given neighborhood, that's some neighborhood that we've defined. What this gives us is the idea that these sequences, the elements of these sequences are getting arbitrarily close to each other. And that is defined as a Cauchy sequence. In a intuitive sense, it's a sequence where the elements are getting arbitrarily close to each other as you go along. An important discussion in sequences in general is about convergence, and this is, we define how convergence of sequences is defined initially. So if I know a sequence is convergent, I can always show that the sequence is Cauchy without doubt in any space. However, if I have a sequence that is Cauchy, can I say it's convergent? It's actually quite interesting, and this is a very important question because this shows us certain behaviors of the space we're in itself. A Cauchy sequence is guaranteed to converge only in compact spaces. A compact space is nothing but a space that is closed. That means that it contains all its limit points. There's no sequence that is if I have a sequence that's converging to some point, that point it converges also belongs to this space. And also it's what is known as bounded. In other words, it's always, this entire space is contained in some finite bounded sphere. So this convergence properties of Cauchy sequences helps us significantly in analysis, and this is why I thought this is an important topic to cover. For further references and more detailed theorems and understanding of Cauchy sequences, the Principles of Mathematical Analysis by Walter Rudin is a good resource. Uh, Thank you.